In this chapter, we're going to talk about something called hypothesis testing, and for this first lesson, we're just going to look at the very basics of hypothesis testing. To summarize the beginning, what hypothesis testing is essentially somebody telling you some claim, and you're going to be able to test it using statistical methods. Let's look at some vocabulary. A hypothesis is a claim or statement about a property of a population, such as a claim about the mean or a claim about the proportion of the population. A hypothesis test is a procedure for testing a claim about a population. The rare event rule is something we've come across several times so far. It says that if we observe a rare event in a sample, we conclude that our original assumptions were incorrect. So for example, if we assume that for some procedure we will get a higher than 50% chance of having a girl versus a boy in a birth, and we test that with some sample data, if we get a lot of girls that would otherwise be unlikely or rare, we can assume that our original assumption or our original hypothesis was incorrect. So for example, a company claims to increase your chances of having a girl, a method they call XSort. If we look at 100 couples in a sample using this method, what can we conclude if we observe that 52 couples have girls? Well, just intuitively, and we'll come up with more exact methods for testing this, but just intuitively, if we had 52 out of 100 couples have girls after using this XSort method, we would not jump to the conclusion that this XSort method actually works. Because if we didn't use this XSort method, we would expect about 52 couples to have girls out of 100. However, if instead we observed 97 had girls, now this is very unlikely if this XSort method didn't work. So according to the rare event rule, we observe something that would happen very rarely, so we can assume that it's not just a 50-50 chance now, and that this XSort method actually does work. So a little bit about notation. In the previous example, we assumed that P equaled 0.5, so we didn't state it explicitly, but we assumed that the proportion of girls you would expect to get out of all births would be 0.5 or 50%. So without treatment, there would have been a 50% chance of having a girl. P greater than 0.5 indicates that this method was effective, because that's saying that the proportion of people who are using this method and get a girl is greater than 0.5. Or in other words, there's greater than 0.5 chance of having a girl using this method. Also, notice that what we're going to be talking about in this section is not the probability of getting an exact amount. So we're not going to talk about the probability of getting exactly 13 girls, or in the previous example, the probability of getting exactly 50 girls. We're talking about probability of 13 or more, or in the previous example, 50 or more girls. Because that would indicate the probability was greater than 50%. So we're not going to be looking at these exact probabilities. We're going to be looking at what we call the probability of getting something more extreme than a number. So either greater than or less than a specific value. A couple other terminology notes. The null hypothesis, what we notate as H sub 0, is a statement that the population parameter is equal to some claimed value. So a null hypothesis might be P equals 0.5. The proportion of girls equals 0.5. Now keep in mind, the null hypothesis will always have the equal sign associated with it. So let's get these examples. The mean income of bankers is greater than 60,000. If we wanted to get a null hypothesis from this, instead of going a mu is greater than 60,000, we would say mu equals 60,000. So our null hypothesis, our statement that our parameter is equal to some claimed value, is that the mean equals 60,000. Number 2, the proportion of people aged 18 to 25 who use drugs is 0.2. So here, my null hypothesis is P equals 0.2. So one thing to note about the difference between example 1 and example 2, our null hypothesis in number 2 happens to be the same as the statement we had. The proportion is 0.2, so our null hypothesis is P equals 0.2. Whereas in example 1, the mean is greater than 60,000, but we had to change our null hypothesis to be an equal statement, mu equals 60,000. So look at example 3 here. The standard deviation of duration times of Old Faithful is less than 40 seconds. So again, we want a null hypothesis to be an equal statement, so we're going to change this to standard deviation equals 40. Now let's take a look at identifying the alternative hypothesis. So the alternative hypothesis is denoted by H sub 1 or H sub A in some cases. We're going to stick with the H sub 1, but the text you're reading might say H sub A. In either case, that's the alternative hypothesis, which is a statement that the population parameter is different in some way from the null hypothesis. So recall, with the null hypothesis, we always used equality. With the alternative hypothesis, we're going to use less than, greater than, or simply not equal to. So let's look at those same examples. The mean income of bankers is greater than 60,000. We said the null hypothesis was that the mean equaled 60,000. The alternative hypothesis in this case, based on this statement, income of bankers is greater than 60,000, we're going to use the greater than symbol. Number 2, the proportion of people aged 18 to 25 who use drugs is 0.2. So recall, when we found the null hypothesis was what came from the statement. So the null hypothesis was that the proportion of those who use drugs is, or equals, 0.2. So since we have no indication of greater than or less than from our statement, our alternative hypothesis is simply going to be not equal to. So number 3, the standard deviation of duration times of Old Faithful is less than 40 seconds. So because the statement says less than, our alternative hypothesis will be less than 40. Let's take a look at an example where we identify the null and alternative hypothesis. An airline company claims that the mean weight of airline passengers is at most 195 pounds. So let's first of all identify the claim and write it in mathematical symbols. So the clue is at most 195 pounds. At most means that it can't go over 195 pounds, but it could be equal to 195 pounds. And keep in mind, in this case, we're talking about a mean as opposed to a proportion. So our claim is that the mean is greater than or equal to, less than or equal to 195. Because at most means it can be up to 195, but it wouldn't be greater than. So it's less than or equal to 195. The opposite of our claim is simply the mean is greater than 195. So in other words, the opposite of less than or equal to is greater than. Step 3, we're going to choose the statement out of those two, the claim and the opposite. We're going to choose the statement that includes an equal sign, and if necessary, change it to just equals to be our null hypothesis. So our claim was less than or equal to. We're going to change that less than or equal to into simply equals and call that our null hypothesis. The other statement, in this case, it's our opposite, had no equal to statement, so that's going to be our alternative hypothesis. We're going to be talking mainly about means and proportions and claims about those two. If we're talking about a mean, we're going to have a test statistic calculated by this formula. And if we're talking about a proportion, we'll have a test statistic calculated by this formula. So just a quick run through, the x bar will be from our sample, and that'll be the mean of our sample. This mu, in this case, is going to be taken from our null hypothesis. So our null hypothesis is always going to be mu equals a number. That number would go into here. So we'll have a sample mean, and we'll have the population mean from our null hypothesis. And we'll have our sample standard deviation, which will take the place of S. And we'll have square root of n, of course, n being our sample size. For our test statistic for a proportion, p hat is our proportion from our sample. P will be the proportion from the null hypothesis. So again, the null hypothesis in this case would be p equals some number. And then underneath the square root, we'll have p, again from our null hypothesis. Q, you could guess by this point, Q would be 1 minus p. And again, n will be our sample size. Consider the claim that the XORT method improves a couple's chance of having a girl. Calculate the test statistic if we conducted an experiment with 14 births using this XORT method and 13 of them resulted in girls. So first of all, let's consider the claim. The XORT method improves a couple's chance of having a girl. So I want to identify the null and alternative hypothesis. And to do that, using this claim, I have to write this in symbols. So if the XORT method improves a couple's chance of having a girl, that means they're saying of all the people who use this XORT method, over half of them would have a girl. So that is, our proportion of girls is greater than 0.5 is the claim. Step 2 then is to identify the opposite. The opposite of a greater than statement is less than or equal to. So our opposite statement is p is less than or equal to 0.5. Now to use this information to get our null and alternative hypothesis, you have to identify which one has the equals statement in it. And of course the less than or equal to has an equal statement in it, so that will be our null hypothesis, p equals 0.5. The other one, p is greater than 0.5, will be our alternative hypothesis. So now to calculate the test statistic, we just have to plug in what we know from our sample and what we're using from our claim. So that is p hat we would get from our sample statistic, 13 divided by 14. P is going to be our claimed proportion, or rather our null hypothesis proportion. P equals 0.5. Then we can get 0.5 and 1 minus 0.5, which also happens to be 0.5, for the denominator of our test statistic. And of course, n is our sample size, which was 14. So plugging all this into the calculator gets us 3.21 as our sample statistic. A little more terminology. A critical region is the set of all values of the test statistic that would cause us to reject the null hypothesis. So these will be the extreme values of our test statistic. The significance level is the probability that the test statistic falls into the critical region when the null hypothesis is actually true. A critical value is a value that separates the critical region from the rest of the probability distribution. So let's take a look at a normal distribution graph and identify where those three terms that we just mentioned are located. That is the critical region, the significance level, and the critical value. So if our significance level was 0.05, then if we're talking about our normal distribution with two tails, as we were in the previous chapter, we would split that significance level up between the two tails. So here my significance level is 0.05, and I would have 0.025 in both of those tails. The critical region are these values down here that if my test statistic falls into one of those critical regions, I would reject my null hypothesis. The critical value is that value that separates this critical region from the rest of it. Now, of course, in this case where we have two tails, our critical value is specifically the positive version, but we would also have a negative version that would separate the bottom critical region from these upper, more normal values or more expected values. But for calculation purposes, we're only considering the positive version of this critical value. We'll see here in a second, sometimes we're only concerned with one tail of our normal probability distribution, or our t-distribution. In those cases, if our significance level is 0.05, we don't have to split that up into the two tails. So that means our significance level, alpha equals 0.05, stays all over here in the left tail. In other words, this shaded region that I have here is 0.05, and I would have 0.95 to the right. So this is slightly different than what we've been doing, and we'll see where we'll use this in a moment. But in this case, our critical region is just these values over here on the left. It looks like from about 0.1645 maybe on down below. So our critical value then is 1.645. Even though we're in the negative region, for calculation purposes, we're going to use a positive 1.645. The question we now have is, how do we know when we're dealing with two tails or just one tail? And the answer lies in our alternative hypothesis that we came up with earlier. So for a left tail test, we would have this if our alternative hypothesis had a less than symbol in it. In that case, we're dealing with a left-tailed test. Otherwise, we might be dealing with a right-tailed test, and this, of course, is if our alternative hypothesis has a greater than symbol in it. And lastly, we're going to be dealing with a two-tailed test if we have the not equal sign in our alternative hypothesis. So for example, let's use a significance level of 0.01 and find the critical z-value for the alternative hypothesis p greater than 0.5. So here we know it's one tail, and more specifically we know it's a right tail test because we're using the greater than symbol in our alternative hypothesis. So here our critical value is 2.33, and we get that from noting that our significance level is 0.01. We don't have to split that into two tails because this is a one-tail test, so we simply have to look up the z-value that has 0.99 to the left of it, which will be the z-value that has our 0.01 to the right of it. So look that up in your normal distribution table and see if you don't come up with a critical value of 2.33. Let's use a significance level of alpha equals 0.1 to find the critical z-value for the alternative hypothesis p not equal to 0.5. So here, because our alternative hypothesis is using a not equals, we know that it's a two-tailed test. So now we have to split up our significance level 0.1 into two tails, and that is we'll have 0.05 in one tail and 0.05 in the other tail. So I want to know the critical z-value that separates 0.05 from the rest of this. That is the critical z-value that has 0.05 to the right and 0.95 to the left. Well, of course, this is the critical z-value 1.645. But look it up in your normal distribution table to verify. One method we're going to talk about in the next section is something called the p-value method. And this is the probability of getting a value at least as extreme as the one representing the sample data. So for example, if we're talking about proportion, and I get a proportion of 0.7, I want to know what is the probability of getting a proportion in sample data that is at least 0.7. If the test is one-tailed, and p is greater than something, then the p-value is the area to the right of the test statistic. However, if it's a left-tailed test, then we'd say the p-value is the area to the left of the test statistic. So for example, if I had a test statistic that gave me a test value here, the area to the right of that test statistic would be my p-value. If the test is two-tailed, so we have an alternative hypothesis that gave us a not equals, then the p-value is twice the area to the right or left of the test statistic, because we have to account for the other tail. So if my test statistic is here, then not only do I want to count the area to the right, but also the area to the left to account for the other tail, and that is the probability of getting something more extreme, either on the right side or the left side of my normal distribution. Consider the claim that the XORT method of gender selection increases the likelihood of having a baby girl. Suppose sample data resulted in a test statistic of z equals 3.21. Calculate the p-value. So we're going to calculate the value to the right of 3.21, but we need to know if we need to double it or not. So the first thing to do in a situation like this is identify the alternative hypothesis. So to do that, we first need to identify the claim, which in this case we're saying the XORT method increases the likelihood of having a baby girl. So our proportion of girls would be greater than 0.5 is the claim. The opposite of that is p is less than or equal to 0.5. Our null hypothesis is going to be, we're going to get that from the p is less than or equal to 0.5 because that is the one that has the equals in it. So that means our alternative hypothesis will come from the other statement, in this case the claim p is greater than 0.5. So now that we know what the alternative hypothesis is, we know this is a right-tailed test. So we're dealing with this right-tailed test, and now I need to calculate the test statistic, the p-value, that is the area to the right of my test statistic, 3.21. So I need to find the probability that a z-score would be greater than 3.21. That is going to be the same, of course, as 1 minus the probability that a z-score will be less than 3.21. So I need to find the probability that z is less than 3.21. Looking this up on my normal distribution chart and taking 1 minus that, I get a value of 0.0007. Suppose the claim instead is that the likelihood of a girl after using the XORT method changes the likelihood of having a girl. So notice, instead of saying increases, I said changes the likelihood of having a girl. So I don't know if the claim is saying increases or decreases. And then suppose sample data resulted in a test statistic z equals 3.21. Let's again calculate the p-value. So again, first of all, we'll identify the null hypothesis, the alternative hypothesis, but first we have to get the null hypothesis. So the claim in this case is that p does not equal 0.5. Because all we know from the claim is that it changes the likelihood of having a girl. Whether it increases or decreases, we're not saying. So the opposite of this statement, a not equal statement, is that p equals 0.5. So our null hypothesis will be the statement that has the equals in it, in this case p equals 0.5. And our alternative hypothesis will be the other one. In this case, p does not equal 0.5. So we have our alternative hypothesis, and it has a not equal statement in it. So we're going to use a two-tailed test. So we're looking at this two-tailed test, and what we want to do is calculate the value to the right of our test statistic 3.21. That'll be our p-value, except since it's a two-tailed test, we also have to calculate the probability that our test statistic would fall this far out to the left. So that is, the p-value is going to equal 2 times the probability that our z-score is to the right of 3.21, which is 2 times the 1 minus the probability that our z-score is to the left of 3.21. And like we found in our previous problem, the probability that z is less than 3.21 is 0.007. So we multiply that by 2 and we get a probability of 0.0014. So our p-value in this case, because it's a two-tailed test, is 0.0014. So a couple things to note. We have two options when we're hypothesis testing. We can either reject the null hypothesis or we fail to reject the null hypothesis. So we never say we accept the alternative hypothesis. We either say we reject the null hypothesis or we fail to reject the null hypothesis. We're going to talk about, in the next section, 3 different methods that will help us determine whether we reject the null hypothesis or fail to reject the null hypothesis. And those are the p-value method, the critical method, which is also called the traditional method, and the confidence interval method. The p-value method tells us that if the p-value is less than the significance level of the problem, we're going to reject the null hypothesis. Otherwise, we would fail to reject the null hypothesis. With the critical value method, if the test statistic falls within the critical region, we're going to reject the null hypothesis. And otherwise, we're going to fail to reject the null hypothesis. And lastly, if a confidence interval does not include the population parameter, we're going to reject the null hypothesis. So just as we were doing in previous sections, we're going to find confidence intervals based on our sample statistic, and if that interval is too high or too low and doesn't contain the parameter that we're saying h naught that parameter equals, then we're going to reject the null hypothesis. Otherwise, we'll fail to reject the null hypothesis.